Welcome to another exercise for this workbook statistics. This time I'm going to talk about measures of contingency. So more or less measures of association, but for normally scaled variables. Our exercise here, a hotel questions its customers about the services they like the most and differentiates in this regard between the genders. In the last month, the following data has been collected. And we get this data for three parts: the bar, the restaurant and the animation, divided by male and female guests. Our tasks now: use a suitable measure of association normalized to the interval 0 to 1 to quantify the strength of the relation. So here we could use different alternatives. All of them would start with calculating chi-squared. So that's our first step. If we want to get chi-squared, we're first going to add to our table our marginal frequencies, so the row and column sums and the overall number of observations. So here we're just going to add these two, and down here we're adding those three. Finally, down here we're adding up all of them. So here that's the sum for the male column, the sum for the female column. Then we're going to do the same thing for the rows. And in total, we get 220 observations. That's actually the numbers we need for the next step, because based on those marginal frequencies, we can calculate the expected frequencies under the assumption that all the values here are evenly distributed, following only the marginal frequencies. So I'm going to copy the table from before, but I'm leaving the parts in between here blank. And then I'm using this formula over here to calculate the expected frequencies. This might look strange at first glance, but what I'm actually doing here, if I'm working in this field, I'm just going to pick the corresponding value for the column and the corresponding value for the row. I'm going to multiply those two and divide them by the number of observations. So here I get 48 times 110 divided by 220. So I can imagine this like a large rectangle, and I'm going to calculate always for each of these values in this corner by using those connecting corners divided by the opposing corner. So as I said, 48 times 110 divided by 220, giving me 24. Now I'm going to do the same thing here. 49 times 110 divided by 220. 131 times 110 divided by 220. And for females, the same thing. Here I'm always going to use this 110. So we see here these 110s are the same as here, same one there. And the 48, that's those two. 49, that's those two. 131, that's those two. So there's certain kind of structure to it. Well, that's actually the second table we need. Now we're going to compare the original data with the data of these just calculated expected frequencies. That's actually what we're going to do with the chi-squared statistic. Just going to copy the table or the values I had before. First off, the left values are the original ones. The right values are the expected values. And then to calculate chi-squared, I'm going to use this formula. So this is always expected value minus actual value, in parentheses, squared, divided by expected value. So the first one is 24 minus 34, in parentheses, squared, divided by 24, the expected ones. And then I'm going to do this for each of my 6 entries. Here I'm just written this down step by step by step. If you actually want to avoid losing track of what did you already calculate, what didn't you yet calculate, you could also simply use again the same table layout as before and then just do this for each of the different fields and afterwards add up all the entries in this table, because this is what those two sums actually mean. Calculate this expression and then sum up across all columns and all rows. And that's it. So we're going to calculate these chi-squared parts for each of these different fields, adding them up, giving us a final result of 21.1574. Well, this is not normalized to the interval 0 to 1, because this is definitely larger than 1. So we need to normalize this. Here we have different alternatives. One would be, for example, Cramer's V. We could be calculating the phi coefficient, or what we're going to do here is the contingency coefficient. So for the contingency coefficient and the corrected version thereof, we're going to use the chi-squared we just calculated, and then we're going to use the following formula. So chi-squared divided by chi-squared plus the number of observations. Number of observations here was 220, so we're going to divide the 21 by 21 plus 220, like this, and taking the square root thereof. So this is 0.2992. This already usually is smaller than 1, but this is not an indicator between 0 and 1. So that's a problem, meaning we have to correct this first before we can halfway decently interpret this. And that's by multiplying this with a correction factor. For this correction factor, I have to calculate this helping value m, which is just the minimum of numbers of rows and numbers of columns. Well, here I have 3 rows, 2 columns, so the minimum of the 2 is 2. And then with the m, I can calculate this correction factor m divided by m minus 1, square root thereof. So here I have 2 by 1, well, multiplied with the square root of 2, gives me an end result of 0.4189. This is actually a value I can interpret. Similar to the other statistics, measures of associations I had, here I can say, well, this lies somewhere between 0.3 and 0.5. So that's a relation of medium strength. Well, that's then it about this exercise. So I hope you enjoyed it. I say goodbye and see you next time.